Hello, my name is Bruno Carl, and I'll be taking you through my poster presentation on data-constrained modelling with multi-energy X-ray computed microtomography to evaluate the porosity of plasma-sprayed ceramic coatings. Plasma-sprayed ceramic coatings exhibit multi-scale void networks, which include macropores, as shown in Figure 1A through E, which are in the micrometer range, micropores, shown in Figure 1G, that are within the nanometer range, and fine structure microcracks, as shown in Figure 1F. The void networks tend to have a negative impact on coating mechanical and thermal properties, and hence the accurate evaluation of voids is vital in predicting the functionality of coatings. The data-constrained modelling technique employed in this study has a significant advantage over traditional micro-CT image segmentation techniques, as it can incorporate fine structure details below the CT resolution and hence evaluate micropores and microcracks. This is illustrated in Figure 2, where a portion of a monophase coating on a substrate has undergone modelling using typical CT techniques and the DCM approach. Each voxel that comprises the CT model will be assigned a specific phase, even though it may be made up of several phases, including voids. Whilst in the DCM model, the voids within each voxel are assessed, allowing the evaluation of voids below the CT resolution limit. Thus, the work presented here demonstrates that the DCM methodology can quantify compositions within scanned samples that incorporate porosity with a moderate CT resolution, which was 5.4 micron. Coatings of the materials zirconium boride and hydroxyapatite were deposited via atmospheric plasma spray, and X-ray CT slice images acquired at the Australian Synchrotron Imaging and Medical Beamline, utilising the Ruby detector. Samples of the coatings also underwent a 2D pore assessment via image analysis. Data-constrained modelling was then used to obtain 3D reconstructed models, as shown in Figure 4, and the resolvable porosity of the models displayed in green was inspected. A comparison of the 2D pore assessment of the coatings and 3D resolvable pore assessment of the models was then executed and revealed a large disparity. The majority of the area corresponding to the 2D pores within the ZRB2 coating was found to be within the intermediate area range, as shown in Figure 5. Whilst the vast majority of the volume corresponding to the 3D resolvable pores within the ZRB21 model were within the largest pore volume range, as shown in Figure 6. This disparity is due to the fact that a 2D micrograph or model slice contains no information about the depth or 3D morphology of a void, or whether it is part of a strongly connected void network. However, it was found that the 2D quantification of porosity within the coatings via image analysis was in moderate agreement with the total porosity determined within the 3D models. The difference in porosity quantifications is due to the superior ability of the DCM methodology to quantify fine structure details of micropores and cracks over 3 dimensions as compared to 2D image analysis. Thus, to conclude, data-constrained modelling accurately quantified the porosity within coatings, including some pores below the CT resolution, as shown in Figure 6, even with a moderate CT resolution of 5.4 micron. The 2D quantification of porosity was in moderate agreement with that obtained from the 3D models. However, the 2D pore assessment poorly predicted the 3D morphology of voids. As such, any properties strongly dependent on the 3D microstructure of coatings, such as thermal conductivity, cannot be accurately inferred from the 2D inspection. Finally, an analysis of the models revealed that the DCM approach improved modelling, with up to 91.5% of voxels within the ZRB21 model and 81% of voxels within the HAP1 model identified to potentially be incorrectly modelled if typical CT segmentation techniques had been utilised. Thank you for listening to my presentation. That's the end.